now we go in more details on multivariate normal distribution. So when we are talking about a multi-dimensional, multivariate normal distribution, here is the equation. This equation is a vectorial version of it. So it's more compact. It's quite interesting in terms of being able to express clearly this notion of normal distribution over all variables with one equation. So it's if you look at it and you compare with the one-dimensional version, it is the same basically with some specific elements. First, we see here that we have a covariance matrix. The square root of the determinant of the covariance matrix, which is equivalent to the square root of the sigma in 1D. And we also have this multiplied by the inverse of the covariance matrix here, which is equivalent to dividing by the sigma in the original equation. So if we look at this in 2D, it's kind of easy to visualize this thing. We see that we have, I would say, a distribution here where we have a peak. So we see this that in 1D, in fact, in 3D, we have this thing here. So it is a two-dimension distribution, but the third one, the Z dimension, is about the values of the PDF over the space. And if we look at this in a more planar view with some kind of color over the surface, it is represented by these things. So these are just two different ways to visualize the same thing. So the mean vector, the big mu here, is really at the center. So it's really here at on the peak and on the middle of the distribution here. And in this equation, we are normalizing by the inverse of the covariance matrix. So basically, the covariance matrix gives us the shape and allow us to normalize the distribution over that space. So in 2 dimensions, which is, I would say, a good way to start to visualize this thing, we have this as the parameters of the 2-dimension Gaussian distribution. We have a mean vector with 2 values, and we also have the covariance matrix, which is built of the variance over variable 1 and 2. And we have on the diagonal the same values, which is the covariance between x1 and x2. And this corresponds to the correlation times the standard deviation for x1. So we have like correlation, standard deviation of x1, standard deviation of x2. So we are multiplying these 3, that is equivalent to the covariance. With this, we can see there are like 4 possible cases for the covariance matrix. First case would be with a diagonal covariance matrix that is equivalent to a correlation of 0, a row of 0. So in such case here, these things are equivalent to 0 directly. And we can also look at the diagonals. And if we have diagonals that are equal in both directions, we have what we call an isotropic case. And as such, we have really a round circular distribution, completely circular, equal on all directions. So that is the first case. The second case, again, the matrix is diagonal, the correlation is 0, but we have different variances for the 2 dimensions. We have sigma 1 square, sigma 2 square here, which are not equivalent, but which are describing so different variants over the dimensions. So this is corresponding to distributions that are more like along one or the other of the variables. If we have positive correlation between the variables, we have a case where it will be shaped in one way. And likewise, we can get also negative correlation. So these 2 cases are with non-zero values of the diagonal. So that is describing distributions that are in different shapes. So to illustrate this here, we have really the first case. So everything, so correlation is 0. So we don't have any correlation. All values are equal on both sides. This gives us a really circular view of that. So this is really the distribution in 2D, and the 3rd dimensions is coming out of that picture. So closer to the center, higher is the value. So these are like contour curves of the distribution. So in that case, this looks like this. In the second case, we can see here a case where sigma 1 square is higher than sigma 2 square. So that means that we have more variance toward x1. So the distribution is longer, is organized more like in a to be more spread over x1 compared to x2. And if we had the opposite, if sigma 2 square were higher than sigma 1 square, it would have been more spread toward x2. But still here we have correlation of 0, so that means that the spread is either along x1 or x2, not differently. Now, if we have a positive correlation, now what we see is that this distribution is kind of skewed, is kind of having a slope that looks like this. So this is with a positive slope in terms of the spread, the main direction of the spread of the covariance matrix, also from the points, the values of that distribution. And if we look at the other case where the correlation is negative, that's pretty similar, except that the directions where the distribution is more spread is with a negative slope. So if we look at the values of the determinant of the covariance matrix, we can get a good indication on the proximity of samples around the mean. So if we have a really low value, so if the determinant is low, that may indicate a high correlation between the variables. So the variables are kind of correlated together, maybe just according to few dimensions, but still a high correlation is obtained, is there. Generally, when we get a covariance matrix that is symmetrical, positive, definite matrix. So otherwise, when we get a singular matrix, the determinant is 0. So that means something. That means that we may either have a linear dependence between the variables. So that means that at least a pair of variables has some kind of linear dependency, such as we can basically remove all dependent variable except one. So we just keep the independent one case of when we have pairs or more variables that are dependent together, because it is over-representing. These are completely dependent from each other. So these are not useful in terms of modeling what we are looking for. The other case is when we have variables where the variance is 0. That means that the value is all the same for all samples. That may happen. So in such case, we'll get a determinant of 0. So that's another pathological case. And in such case, we can consider to remove also that variable, given that we don't get any variance there. There is no variation on the value. So also another interesting thing is that if we have a vector x, so this is our vector, which is following a normal distribution of d dimensions with the mean vector mu and covariance matrix sigma here. So if we have this x, then we can see that each component of x, which are the xi, so variable xi, is also following a normal distribution, which has a mean of ui, which is expected, but also has a variance of sigma I, but tilde, so it's not exactly the value on the diagonal. If the value, if we have x's that are independent, in the case where we've got only a diagonal matrix as covariance matrix, all values out of the diagonal are equal to 0, or said otherwise, we have no correlation between the variables. Then we know that xi is following a normal distribution in 1D with a mean value of mu I and variance of sigma I squared. If we are applying some kind of linear projection, so we have a vector W that is making a linear projection from in a space in k dimensions from an original space in d dimensions, we know that our result, so the results of W transpose X here that we have, which is the result of the projection, is also following a normal distribution with of k dimensions. which normal distribution is characterized with a mean vector of W transpose mu here. So it's kind of applying the linear projection on the mean vector directly to get the new mean vector in the new space. And the standard deviation is basically W transpose sigma W, which is giving us the new covariance matrix in that k-dimension space. Even more, if we are looking at conditioning some given multivariate normal distribution, we get interesting results. We also obtain multivariate distributions. For example, here we are starting from, this is the original distribution in 2D. You see that we have a normal distribution which has a negative correlation here, given the slope that is like this. If we do a conditioning, saying that, for example, if we are looking at the case where x1 is equal to 0.3. So this is the condition. We just look at the distribution of the x2 when x1 is equal to 0.3. So it's basically to look at that slice here. If we look at that slice, the data that are all projected, so we are not considering other x values. We are looking only at the distribution of points that we would obtain there with x1 equal to 0.3. We have this kind of distribution, which is relatively narrow and has a mean vector around, I would say, 0.65, 0.67. If we compare this with the distribution of x2 without any condition, so the distribution over the whole domain here, we can see that the spread is much higher, and that corresponds to the I would say the view of that the whole distribution, but only from x2. Likewise, if we are looking at the spread of x1 without any condition, so we are looking at the whole domain here, we have the black curve here, which shows us a big distribution. And if we are looking at the condition of x2 equal to 0.7, which is basically the slice here with the red line, if we're looking at that slice, we see that it is basically concentrated there. And in such case, we have the red distribution here as our distribution of x1, given that x2 is equal to 0.7. And this is also a normal distribution. So here, the green and red curves are corresponding to normal distribution. Px1 given x2 equal to 0.7 is following a normal distribution. Now, if we look at Mahalanobis distance, this is an interesting use of the covariance matrix. If we assume that we have data distributed according to a normal distribution in multiple dimensions, we can compute what we call Mahalanobis distance, which is not exactly a distance because we are not computing anything, no pairs of value. We are just computing value for a single x, but this is computed according to some normal distribution, and we are looking at the distance or the difference between the x in question versus the mean vector of that distribution. So we are computing the difference between these two, but then we are also using the inverse of the covariance matrix. So it's pretty much like looking at the distance of one point from the mean of the Gaussian distribution, taking into account the shape of the distribution. Like if we are climbing a hill, the cost of climbing that hill is basically is somehow similar to a Mahalanobis distance. So stated otherwise, it is basically the distance between the mean vector mu here versus the point x here, weighted by the covariance matrix. So the covariance matrix is somehow weighting this differently. So we can see here that when we are on a line, so we have this contour plot that is somehow illustrating the normal distribution in 2D without having 3D plots with the x, the z view over it. But when we are on one contour plot, we are at the equal distance. The Mahalanobis distance is fixed there. So all over the other loop here, when we are on the curve, we are at a constant distance, a constant Mahalanobis distance from the center. Likewise, at the second curve, when we are on that curve, we are at a constant distance, and the third curve also, the distance is smaller than the two others and constant all over the curve. So the contour lines correspond to a constant distance c squared. In 1D, the Mahalanobis distance can be simplified as this. So basically, it's x minus mu, so the x value minus the mean value squared divided by sigma squared, which, when just formulated differently, is equivalent to that, and you can see that the correspondence with the vectorial notation is direct.